Hi everyone. Um, Hopefully everyone had a nice week and did well on the homework at 8. I believe only two more homeworks to go, which is pretty good. But yeah, in the meantime, happy to answer anything that was discussed this week. I know mostly the topics have been like trees and hash tables, but even if there's something earlier or just something else you want to ask about, happy to help and discuss. Yeah, sure. Yeah, give me one sec. So I believe you only covered part one, right? So you haven't gone to part two yet. Oh wow, you're gonna have to do it right after hash tables. Interesting. Okay. Yeah, so hash tables are a very interesting concept because it allows us to, it's a certain type of data structure that gives us O of one insertion, removal, and lookup big O, which is something that we haven't quite seen before. So, for example, if we have a vector, right, and we want to find some number in the vector, such as like a 2, and we don't know where the 2 is, worst case scenario, we have to go through everything, right? And then we finally find the 2. It's right here, but, we don't know where that was. So that's going to be an of n search. The best thing that we found so far wasn't, within a linked list or a vector or, an STL list or anything like that. It's been in a binary search tree, which is when we've used, a standard map, right? The STL map as well as a binary search tree, because a map's kind of just a binary search tree in the background. We kind of were able to find things in log of n lookup because what we recognize is if we can have them in this structure, we can basically avoid half the elements as we go down each level of the branch, right? If we want to go find the 3, 3 is less than 5, we never have to look like down anything in the subtree. So that was an improvement. That takes us to log of n, but there is a way that regardless of how big the input becomes, that we can always in constant time know where to find something in a hash table or in a, I'd say a data structure, right? And that would be a hash table. And the way hash tables work is there's kind of two components. There's a container, and it can be represented in many ways. I'll I'll send a couple links of some great practice problems I recommend. And if you can, implement these practice problems, I'd say you pretty well understand the how tables work. And let's say we want to, containerize maybe, I don't know, let's say we want three elements. Well, the first thing I would recommend, and we'll kind of go into more detail of why, is that we leave room for not three elements to put in here, but maybe a lot more. Let's say we put in eight. So one, two, three, four. 1, 2, 3, 4, 5, 6, 7, 8. Right? And the idea with a hash table is if we want to put in a collection of numbers, let's say we want to insert a 3, a 5, and a 7 again. Well, the location we put it in the hash table kind of depends on this function that we put together. It's kind of like an algorithm that will spit out an index of where we can put it. And that's what we call the hash function. And this is very helpful because what it's going to do is take in some specific input that we want to place in the hash table. It's going to perform some algorithm on it depending on what that input is, and it's going to output to us some index to put it in. And this is good because in the future, if we then put this number back in here and we want to see if 3 is in the hash table, well, the hash function is repeatable. It's always going to give us a consistent result for the input. And for that reason, what's going to happen is we'll get access to that place in the hash table in O of one time because what we want is this algorithm here to be constant. So if we take in as input 3 and Yeah, let's say we do some, algorithm in here and we return for now, like say when we put in 3, we return index 2. That means according to our hash function, maybe perhaps we should put the number 3 here. Now let's say we want to put 5 in, and let's say when we hash 5, it turns out this hash function we put together gives us index 0. Well, that means we want to put 5 here, right? And then same with 7, we could put this through the hash function, and let's say we have it here. Now this is good for not just looking up, but also deleting. Now if we want to remove something, like if we want to remove 5 from the hash table, well, it's the same idea. We can just look up where it is by putting it in the hash function. This spits out to us the index. And then we know that indexing something is O of 1. So as long as the hash function is constant and the hash table, which we know looking up is constant, that's still going to be constant. Constant plus constant will give us something that's constant. And the way you can ensure that your function's constant is by making sure it's not dependent on the input size. So if we do some logic with the number 3 or 5 that is based on those inputs alone and would take the same amount of time regardless of how big this table is, if there's 100, 100,000, a million, you know that that's a constant function. And you know it's not as simple as just putting it within a function. You need a really good function. And there are functions that have been designed over years of research and academic research to ensure that you have a solid hash function, because a good hash function needs to be, first of all, repeatable. We can't use like randomization. If we put in 5 and we put that here, and then we do a lookup in the future for 5, well, we better get index 0, right? Because then we can't trust the hash function's repeatable. Then we lose the whole ability of going through the hash function to get exactly what we're looking for. Another very important thing is stuff we put in the hash function should have an equal probability of being in all these buckets. And the reason for that is we want to minimize the risk of collision, which we'll talk about collision in a second, or we might talk about it now. I'm thinking. Yeah, let's talk about collision. So the idea is a hash function in a hash table is really only good if we can trust that the things we're putting down here are going to, say this is like a 15, right? If they're going to end up in other like buckets in this table, right? If we put in, 10 now, that should show up here. Let me make some notes because I also want to talk about rehashing at the end. But what happens now if we put in a number, and it's going to happen sometimes, but the idea here is that we want to minimize the risk of collision. So let's say we want to put in the number 12, right? And it turns out, according to our hash function, when we put in the number 12, we also put another note here, talk about that. It turns out when we put in the number 12, we return index 0. What that means is 12 needs to go here. The problem is, according to our code right now, if we go here, there's a 5. So now if we went to this bucket and we look something up in the future, we'd actually have to look at multiple items. So it's not as instant as before. This is what we call a collision, right? So now we also need a 12 here. Now, when we have a hash table, there's kind of two ways to, technically three ways you can handle collision, but there's two collision algorithms. One is called open addressing, and one's called separate chaining. I believe those are the terms that are used in here. Let's see. Um, I don't think I think collision is going to be the first. Oh, okay, it's talked about here. So there's probing and separate chaining. So the first one's separate chaining. In my opinion, this is the easiest and cleanest one to implement. And if you're given the choice, it might be a little easier to do. So what happens is if you have a collision, right, 12 also goes in index 0, just kind of tag that along here in the bucket. That could be a couple things. And a couple of the implementations, sometimes the professor may like make a linked list. Okay, let's say we put in the number 20, and that's also bringing us to index 0. We can just tag this along. And then if we get to a bucket and we get index 0 and we need to find like 12 and we recognize there's multiple items here, you just iterate through all of them until you see them. Now, ideally, you don't have many collisions because then this becomes inefficient. So you want a good hash function that minimizes collisions. So that's one thing you can do. Another way you could represent this, usually the way I've represented it in code, is each of these buckets isn't a bucket of integers, but it's a bucket of vector of integers, right? So worst case, if there's something already in here, you just push it back. And so then this becomes like I would represent it as a vector of integers. If you have that flexibility, that might be more convenient. So that way you don't have all these things extending in here. You're just analyzing a vector and you can just see, okay, if the size is 1, there's no collisions at this bucket. But if there's something already there and we need to add something, then we can just, look up this index and do a pushback. So that's one type of collision handling. Another one is called open addressing. And there's many different algorithms. There's linear probing, quadratic probing, and then just one for each of, to the 3, to the 4th, to the 5th. But really all it means is we're just going to find the next available bucket based on a particular algorithm. So for linear probing, say we go back here and we remove the 20 and we remove the 12. All we really need to do is find the next available spot. So if we're at 5 and we need to put in a 12 and we realize 12 should be at 0, we're just going to put it at the next available place. And so later on, if we get to this index and it's not there, we're going to just start going down, index by index until we can find the place that we put it. If we have another collision, right, and we need to put it here, we just keep going down, we find the next available spot. That would be the linear probing algorithm, right? It's just I plus 1. We'll talk about the mod n in a second. But there's also, we could do that by different degrees, right? We could go by 1 and then by 2, by 3, and by 4. So it's not always going to be the next available bucket. It just depends on the algorithm. If you need to do the jth probe, really the location you need to put it in, you just plug it into this formula here. And that's really all you need to follow. So for example, for quadratic probing, the first one would be I plus 1 mod n, and then if that's not available, then we would do I plus 2 times 2 mod n, I plus 3 times 3 mod n. And again, the whole idea is we're just finding another available slot. The third thing we can do, which isn't really an algorithm, but something to minimize the risk of a collision, is we can make sure we always have a lot of available slots in our hash table. And what I mean by that is when you build a hash table, not only are you keeping track of what's in the hash table, but you might want to keep track of the percent capacity that it's filled at. So for example, if we have a 5 in here, a 3 and a 7, there's a lot of other slots in here that makes it more likely there's more slots down here that are unfilled than filled, which means sure, the hash function is going to help us ensure that there's a good probability it will go into something that isn't there, because that's why you pick a good hash function that does that. But also just based on statistics, there's a higher probability that it's going to go into a place here that hasn't been filled than it is here, right? There's just more empty slots here than there are above here. And what this means is if we can build a hash table and maintain a lot of empty spots, that also minimizes the probability of a collision. So in your hash table class, you could have this variable called capacity, and then you could have a variable called percent filled or like size, and you could say if if capacity, if amount filled divided by capacity is greater than threshold, and you can set some threshold. So like let's say you say, okay, if we ever exceed 60% filled, what should we do? We just create more buckets in the hash table, because the more available slots, the more places where numbers can be put in, which then minimizes the probability that we're going to have a collision, because we don't want collisions. Now, the one caveat is, yes, I recommend having a threshold, right, where if you fill it to a certain percentage, then we want to put more things in. But keep in mind, if we now add more things in, we have to do something called rehashing. And what I mean by that is, in this hash function, really the way the algorithm works is, let's say we do some, magic and the hash function gives us like a number 113. The final step of every hash function is going to be to give us a number within range of the indexes here. So here we have 1, 2, 3, 4, 5, 6, 7 buckets, right? So that gives us the option of index 0, 1, 2, 3, 4, 5, and 6. So what this means is we actually, once we get that final number, we're returning that result mod the size. And keep in mind, all mod does, if you recall, is basically it gives us the remainder of something. So if we want 3 mod 7, this would give us 4 because if 3 goes into, actually, let's do 7 mod 3. Actually, that would give us 3. But for 7 mod 3, right, once we divide 3 into 7, we have a remainder of 4 left over. So we get a remainder of 4. But the remainder is advantageous because it allows us to, if we divide by the size, we would get a remainder left over of an index from 0 up until the last index in the bucket. So the reason this is important, the reason we need to rehash is if the size when we built this hash function was like, 7, right? And then we make this hash table bigger so that way there's more empty spots so that we minimize the risk of collision. What that means in the future is this algorithm no longer works, right? Because we were doing it where size was equal to 7, but if we increase this hash table and now size is like 20, that breaks the placement of everything in here, right? Because here we were assuming that it was in the right spot because we did the mod 7. But now in the future, if we go look up the number 5, we're going to be doing the same function as before, the same formula, but we're going to be doing mod 20, which again is different than when we did mod 7. We're going to be looking at different buckets. So the final thing you have to do is if you ever add more things into a hash table or you change the size, whether you increase it or maybe even decrease it, what you're going to have to do, and this is an O of n operation, you're going to have to do a for loop through every bucket in the hash table, and you're going to rehash that. And what that means is you need to put it through the hash function again. And then because it's a different size, you're going to get some result here, and you're going to do mod by the new size. And that will place it in the appropriate bucket now. And that means in the future, when you look up something in that hash table, that's going to give you it, with respect to the right size. So just keep in mind, if you change it, you need to rehash. And again, you would probably want to change it if you reach some capacity threshold. So in particular, if we have 100 buckets, and let's say our threshold's 50%, once we have 50 things in here, we want to make sure in the future there's still a really good probability that we won't have any collisions. So we might allocate maybe 100 other buckets. And when we do that, everything that was already in here needs to be done through this function before, but not when it's the size of 50, but when it's the size of 100. So we have to do the mod on the new size of the hash table. One last thing before I go into like the questions or look that over, and that would be probably just there's 2 types of hash tables. There's hash maps and hash sets. So if you're coming from CS1, right, that would be like a dictionary in Python, right? If we have a key value pair, right, let's say these are the letters of the alphabet, so this would be like A1, and order doesn't matter here, so maybe C is now 3 as the second thing here, and then maybe B is 2. When we give it a key, we actually get back a value in O of 1 lookup. Now there's also another type of hash, hash map. There's a hash set, right? In Python, that was just the set where we could put all these things in, no duplicates, and this would be O of 1 lookup to see if something was in the set, to add to the set, and so on. But there's one big catch, and this throws off a lot of data structure students because this looks a lot like what you learned when you learned about STL maps, but it isn't, because with STL maps and STL sets, those were actually log of n. So looking it up in the STL map was log of n. Looking something up in STL set or adding, that was log of n, because that wasn't a hash table. That was an ordered map. By default, when you do STL map or you use STL set, it's using an ordered thing. And because it needs to retain its order in addition to a quick lookup, that's where the binary search trees come in, right? It's using a binary search tree. So sure, it can look up things efficiently, but it values the order of where everything is in there. And the only way we can maintain order is if it's structured as a binary search tree. But that means it's not structured as a hash table. So we won't be able to look things up pretty quickly. Now, another thing is if we want to do the equivalent in C++, we wouldn't do standard map or standard set. We would do the exact same syntax, but instead of map, we call it an ordered map. And it's the same, syntax of everything. It's just a different library. And now we're actually, this is a much more efficient, lookup of stuff in that STL map, but it doesn't maintain its order, right? It's not going to be, if we put things in an STL set and we iterate through the set, we know everything in there is sorted. But now, to ensure it's O of one property, it's kind of wherever the hash table has placed it, which is dependent on some hash function. So with an unordered set as well, if we create an unordered set object, that will lose its order. But again, the lookup here is going to be O of one. So the pros and cons of, and so again, this is a set, this is a hash set, this is a hash map. Hash hash maps have key value pairs. Hash sets have, just a collection of data that can be, looked up in, O of one. The pro of an STL map is it maintains its order if order is important. And the con is its log of n compared to where we use an unordered map in an unordered set. The big O is O of one. But if we care about order, then that's a problem. We would, we can't maintain order because it's dependent on whatever the hash function tells us to place it. So the rule of thumb is if you need to maintain order and order is important in your container, this is the better data structure to use, STL maps, STL sets. And also this is assuming there's no duplicates, right? These don't allow for duplicates. So we're also making some assumption that there's no duplicates, that's like collision. There's ways around that, but the idea is using one of these standard libraries, we're assuming like, no duplicates. But if there is no, order to maintain, then an unordered map and an unordered set end up being better. So let's check the chat window, see if we got any questions. What data structure is a hash exactly? Sorry, I joined that. Is it just a list of linked lists because of collisions? And do hash tables need to be sorted? Okay, so let me answer the second question first, just because this is kind of just similar to what we're talking about. So hash tables don't need to be sorted. In fact, they can't be sorted because the order of the hash table doesn't matter, and it shouldn't matter because the location of things that we put in the hash table is dependent on the hash function, right? And the hash function is always consistent. So if we're in a situation again where we want to hash, 3, meaning we want to put 3 in this hash table. If it tells us we need to put it in index 2, then that means we need to place it there. And if we put something else, somewhere else, it's telling us the place we need to put it. So once we put it in the hash table, it's no longer sorted, right? Because it's based on wherever the hash function told us to place it. And in fact, if we do end up sorting the hash table, that means in the future, if we then want to look up that number, if we want to see where 2 is, we can't put 2 through the hash function when it says, oh, it's in, bucket 1 or bucket 2. Well, it can't be because we sorted it. So we actually lose, um, where that was. So we never want to sort a hash table. On top of that, that's kind of why it kind of suggests here that the hash table, the O of one, unordered maps and unordered sets have the word unordered in it because it doesn't maintain order. We can't ever, sort it because then we lose the location of where the things were based on once we put it in the hash table. Give me one second. I'm just going to get my charger. It's just right over here, and then I'll answer the first question here and then the third one. All right, so if we go back here to that first question, so what data structure is a, sure, yeah, we can look over that too. What data structure is a hash exactly? Is it a list of linked lists because of the collision? So really a hash table can be represented in a handful of ways, but the idea here isn't what the structure is, because it could be anything. You could build a class for it. I was, saying earlier that we could even build like a vector of ints, or we could have a vector of ints, depending on how you want to handle the collisions. But what matters is you have a container where you can put objects in it that you can then look up in that container stuff in O of one. So that's a big hint that this should probably be an array or a vector, right? Or something that is built on top of an array, which allows us to, look up an index in here in O of one. Because the whole idea is if we get a hash function here in O of one, and then we get some index, and then we plug it into here to find the location to put it, that should also be constant, because a constant plus a constant is constant. And what matters is once we have a hash function and we take in some input, the idea is it should return back to us, given some input of what we want to put in the hash table, an index that should be within the range of something within the hash table. And we do that in the end with that mod operator. And so if we put in the number 3, right, and that tells us we need to put it at index 1, we're going to place that in here. Now, because this should be as simple as table bracket, if this function returned, say, let me put it in code, it'll be a little quicker. So it should be something like, table bracket, we need first the index, right? So it's going to be like hash function, we want to add in some number. So let's say we want to add in some number. It's going to be hash function number, and that will return to us some index. And then once we have that index, tables at this particular index should be assigned that value of a number. So that's one way you can just put in the hash table. Now, again, you might not do it this way because it kind of depends on how you're handling collisions, right? Because you were mentioning the linked list, so that could be in the situation where you're doing separate chaining, right? Let's say we put some in the hash function like a 5, and it turns out 5 also says, according to this hash function, that needs to be at index 1. Well, in one scenario, we can do linear probing, or open addressing or quadratic probing, or some of those other algorithms in there. And if we do that, we're just finding the next available thing dependent on some algorithm of what we're considering the next available thing. If that's the case, then the structure we have here is fine, because that means every element in here is just going to be an integer, right? This is just perhaps a vector of integers that's representing this hash table. Or we're building a class, and that class is keeping track of, a class is probably better because the class will have a vector that represents the table as an attribute, but it will also perhaps have the capacity and a threshold, right? And we're talking about if we reach some certain threshold, that will be a reason to rehash and change the size. So that's one thing. And then let's see. So, but if we do the separate chaining, right? Where if we have a collision, we want to just keep this in here. There's a couple things we could do. We could have here a linked list that's often represented in class where we add in the 3 here. If we have another collision in the same place, we add it on here. So once we get here, we have to iterate through. What I've done in a lot of the code solutions that I'll send links to is basically I've made a vector of vector events. So that what that means is if I get to a collision, instead of, even if there's nothing in here, I'm treating tables as a vector. And then at each bucket in the hash table, it's basically like, let's say, a vector of templates, right? Depending on what type's being taken in. And then once we specify the index, we're actually not going to just assign that to none because it's really a vector. It'll be like tables index dot pushback number. And again, this would be if we're doing something like separate chaining, and that would be an approach to doing this. Now, if we think about this as a class in terms of implementation, the attributes would be probably capacity, right? How many are in there? And then basically that might be filled. So this is going to be like the total size, right? But you also need an int to see how many have been filled. So right, so kind of like when you learned about the what's it called the vector implementation, right? If we reached a certain amount, we need to allocate more memory dynamically. And then we might have some threshold, might be a float, right? If we exceed 70% or 80%, we might want to allocate more memory. So threshold might be important. And then the core of this that I'm suggesting above is it might be helpful to have tables as a vector. It might be a vector of, t if we're using separate chaining. Or hold up, let me put this in. Actually, this would be if we're doing maybe like open addressing. And then we might have a vector of t if we're doing separate chaining. Because the idea here is we might want to keep track of certain things. Now, there's other ways we can do this, like we were just saying, we could probably just point to another thing and throw that in. I just think this is a lot cleaner to work with, honestly, because then you're just using a vector and then you can, loop through the vector. It's just cleaner in terms of code implementation. So I guess to answer your question, it kind of depends on what the structure will be. But in the end, I think it would be nice if it's packaged in a class because that allows you to keep, track of that threshold. Let's see. Do we implement our own hash table or function, or is it given in STL, like the collision? So it's both, right? So it's kind of in a situation where you've had assignments where you've used the vector STL library, but then there's, tasks where you actually have to implement the vector yourself. Now, you might need to, in the future, implement a hash table if you want more control over, the limitations, because if you use C++'s, hash table, then you can only do what they offer. But if you want some special hash table, which, as you know in the homeworks, it's always like, well, now you learned about this. Now let's do this with some special like catch or some lick and do it in a funny way. So in that situation, you're absolutely going to have to implement a hash table in the homework in some, interesting way. We can look at some past homeworks in a second to see some, examples of that. But the idea is you would have to implement that. Now, if you did want to utilize the standard library and you had permission to, or maybe it's during an exam or something like that, or in the future, it's just like, okay, yeah, I don't want to reinvent the wheel. You'll probably use those two libraries we were talking about. So that would be, instead of the map libraries, if we want to do a hash map, which is one type of hash table, that would be, the unordered map. Basically same syntax and methods as an STL map. And then if the key's an int and the value's an int, you put that, that idea. And then if we want a set, right, if it's a set of integers, for example, it'd be unordered set with ints within here, just like that. And that would be really the libraries you could use. So kind of depends in terms of, I guess in this class, you'll probably, when you're asked to build a hash table from scratch, you'll do that. Otherwise, I would probably go with the simpler option using an existing library. Just be mindful of what the intention is in class in that scenario. In terms of previous assignments, let's look at spring 22. Hold up. Fall 22. What was it last semester? This takes me back. Yeah, so this was an assignment where you had to take a colored image and build like this hash table to kind of compress the image. It was basically you can use hashing to compress images, and you had to take these colored pixels and make it lower quality and just make it a black image, which would store less memory. But if you want to quickly see what that color was, you could look it up in a hash table. And so there was like a hash table. There was also this offset algorithm, and you had to read this paper and understand it. Now, keep in mind, it's different every semester, so it's gonna not be that. So if we look at RPI data structures, spring 2022, let's see what that one was. Was it ropes? Oh no, it was IMDb. This is actually probably a more simpler one. It's really straightforward in terms of you just have to, it tells you exactly what you need to do. I think last semester's was probably a little more tricky, but you're given some information about movies and then you want to look it up in an efficient way. And so that's just keeping track of that in a hash table. Let's look at like one more. Let's look at fall 21. They always change the URL sometimes, but 2021 to like 2015, it's always the same. Fall 2021. Actually, springs are probably more consistent because you have the same professor in the spring. It's always the same, professor in the fall. Oh yeah, this was one of the toughest data structures homeworks I've ever seen, actually, too. Yeah, fall gets it pretty rough. I'm not gonna lie. I remember this. This is probably the toughest. And when I interview people, if they're going through Troy Tutors or Collab Lab or Goro, and I ask them like, "What was the toughest homework assignment you've ever done?" A lot of them who've taken this say this over like the homework six. This was a tricky one. I also saw something similar to this in like a SpaceX take-home project, which was pretty tricky. But I remember this homework assignment being tough. But I would again go look at spring stuff. That might be more consistent to what you would expect your professor. Let's look at one more. So RPI spring 2020. And maybe it's a little different because the pandemic, but for the sake of it, let's assume it was prepared. We just look at one more. And again, I kind of recommend these things if you ever want to get a actually, looks like they reused the IMDb hashing this time around. Interesting. Anyways, interesting things to look at. So hopefully that answers your question in terms of if we have to, implement our own hash table. Part of that depends on the assignment, but most likely, yes, you'll probably be implementing it. But you can use the unordered map when you're allowed to, and that will probably make the most sense in practice, unless you need something, very special. But you shouldn't ever have to reinvent the wheel. If it's something within the programming standard library. Now, if it's the case in software development practice where you're bringing in an external library and it's something you could argue, well, I could do that code myself. It's probably better to write the code yourself because in the future that library that you're dependent on might become deprecated, right? Or something may go wrong, or you can't always assume that that will be around. So it's a lot safer at that place at that period of time to just build it yourself for the sake of cleanliness. Anyways, can we also go over the first problem in the practice problems for test three? And also ways to approach recursive problems. Sure. And have a lab on it. So in terms of if you're being tested on hash tables or not, assuming that I think that's what you're asking. So although I'm not in the class, consistently, that's typically how it works in data structures, right? Exam three, you're tested on hash tables. In fact, let's look at the most recent lecture. They typically say, here, let's go here to confirm. I imagine, and I think another student did mention that it would be on the exam, right? Isn't there usually some paragraph like exam three coming up? Here's the rules. Yeah. Um, but interestingly, it doesn't say if it's going to be in it. Could someone here provide that confirmation? Up to lecture 19. Interesting. Okay. So if that's the case, we go back here. Okay, so fortunately, it seems like hash tables won't be on the upcoming exam, which okay, that's fair, but it will be on the final exam. It's a pretty important topic. Sometimes, most of the times, I've seen them on exam threes, but yeah, it might just be the timing of just when the lectures were carried out this semester. Okay, cool. So yeah, to answer your question, it looks like hash tables won't be on there, but again, it'll be a big part of the final exam. Anything that wasn't yet covered that you weren't able to be examined on does make up a big portion of the final exam. Yeah, thanks for clarifying that. Okay, so the first problem for test three, let's see what that is. It's a recursion problem? Okay. In this problem, you're given a vector of strings representing donut flavors. You can assume they are unique in that the vector is not empty. Fill in the call, fill in the driver function, and then implement your function, which can be recursive and modifies the vector argument to contain all the possible ways to arrange a box with one of each flavor of donut. So if we have a vector of strawberry, chocolate, and maple, it's showing all the possible combinations. Got it. Okay, so this is like a brute force recursion. Okay, let's think about this. So here's what I would think about in a problem like this. One thing is we want to try all possible combinations with, this is what we call actually like a bottom-up approach. But let's put this on the code board and kind of just think about this for a little bit. Now, in practice, this is probably a very inefficient way to do this. You'd use something called dynamic programming in this particular type of problem. Again, this is the driver function that we'll call it, but again, it's going to basically be throwing these things in as input. So if we had, not even think about flavors, let's simplify it to just numbers. And we want to see all the ways we could organize three numbers. Three numbers is typically easy to work with. Well, what we need to consider is the fact that every number here should be a starting point, right? If we need to see every possible combination. So we do want to try it, we want to try this, go down this journey where we're doing it with V0 as the first one. We're probably going to want to try it with V1 being the first combination. And then we're going to want to try it with V2 being the combination. Okay. And if we go down this path, right, that kind of only leaves us the options of all the others. And what that means is we need to try it with every other possible combination, right? So if you think about this, let's say it's of size 3, just like we were seeing, right? We're going to have one for V0. We're going to have a path for V1. And we're going to have one for V2. And if we go down this V0 path, because that's the first one, that really leaves us here with two other places to go. We could either go down V1, and again, this is us just conceptualizing it. With something like this, it might be helpful to draw out the tree, right? We could either go down V1 next, or we could either go down V2 next. Okay, that makes sense. And again, the whole idea is, the reason is because we want this order, right? We want to go in a particular order where it's all the possible ways, so we can't really have any duplicates or repeat anything. So that's for sure one thing we need to consider. And then lastly, if we did V0 and then V1, that only gives us one option left, right? It's going to be V2. So I'm also noticing some pattern here where at each level in this tree, there's one less branch. So that's something to think about. Okay, and if we did V0 and then we go to V2, that kind of leaves us with a V1. This is starting to give me some ideas, right? Let's repeat this here, right? If we were to go down V1's path, and then after this, we kind of just want to think about how can we generalize this to, one, when it's 4 or it's 5 or, so on. So it's going to be V1. In this case, we got to try it with either V0 or V2. Yeah, so something like that. And then that leaves here, right, V2, really the opposite path that we, the one we didn't go down. This would be V2, this would be V0, and you get the idea. It'd be the same as we go down this other path. In other words, this would be, if we go to V2, it's going to be either V0 or V1, and then if we go down V0, that leaves us with V1. If we go down V1, that leaves us, with V0. This is when it's of 3. And if we kind of generalize this by just thinking of one more example that we won't draw out, but if we had like 4, it probably makes sense that we wouldn't have V0, V1, V2 now, right? We'd have V0, V1, V2, and V3. that gives me some hint that somewhere in here to start, we're going to have like some, for I in range, right, for each index in, well, basically, if this is, uh, so we're seeing boxes, right? So in boxes dot size, then whatever that index is, that's going to be our first, scenario. So boxes I will be the first one. But if boxes I is the first one, we need a way to kind of check to see what the next available one is. So let's go back here. So we know that's how to carry it out. And then when we go down that path, we need to make sure to consider the other ones in possibly different ways. So that's going to be a loop two, where we kind of now go through everything that's still left in the box. So that means if we don't want to consider V1, what I'd recommend is now thinking of this as a box where V1 isn't in it, right? We remove it from the box, and then we do a for loop through all the things that are still in the box. So now we can say, well, what happens if we recursively go down the path where we're considering V0? Well, if we do that, then we want to remove V0 from the box, and that kind of only leaves us with V2 at the next level of that recursive stack. And then we could ask that question down here, well, okay, if in the next level of the recursive stack we don't have V1, right, because we recursively called it where V1 was the first, so then we remove V1, and then we're passing in as input V0 and V2, then really we have to do a recursive call on both of those. And when we do that, we remove that one from the box. So I'm also getting this connection by looking at this that, or making this realization that we'll probably need to remove stuff from the box before we pass it down to the next level. And then when we're at that level, we can do like a for loop through and do a recursive call for all the remaining things in that box. So what that would probably look like is making a connection of what's currently in the boxes, right? These are the vec. Let's look at the types in more detail. So I believe box would be, what is box? Current box. Again, I'd argue we don't quite need current box, but I get why it's in here. Really, box is what is, I think, printing six box. Oh, okay, I see. Because right, right. Because the other thing is we don't want to have any duplicates. Now, if we go down this path, we actually won't have duplicates, but this is a very helpful way that if you remember, if we, like you saw in homework 6, if we have a vector of solutions and we pass it in by reference, later on, if we output something that was already a solution, then we can basically see that, we can basically make the assumption that we shouldn't print that out too because we've already found this solution before. Now, keep in mind, that because this is a tree, right, a graph with no cycles, we won't have that problem. Though you could argue it's more efficient to look for that, so we can put that in too. Now box, this is going to be, I believe, the collection. So boxes, let's see, current box. I'm just thinking, do we need current box? So we do find boxes, we take in a box, boxes, and then we're looking at the current box. Let's kind of look at it like this. We have as input here, I don't think we'll quite need the current box in this implementation. We could basically, first, we want to figure out what are all the things we have to consider within this, right? Well, how do we see what's in a box? Let's look at what the box object says. Do we have a class definition for box? Donut box donuts. Do we not have a definition of what donut box is? Then we don't know which attribute to quite get. Um, I mean, we can make an assumption. Let me go back here. Oh, okay. Is in the first line? Oh, got it. It's just the vector strings. I thought it was a special class. Got it. Fair. Okay, so I mean, if that's the case, then we can, loop through everything in the box and see what we're left with. So the idea here is each time we go through, this actually would be very nice without a hash set because we could remove it. But the idea is we want to recursively go through find boxes where in the first time around, right, it's every we're starting with every possible combination. So we want to do find boxes with donut box here where the current box is. So it'd be we want to maintain, I guess, the box of things that we want to look at, but it's going to be the entire box except the one we're currently going to go look at. So that would be box dot. Let's just see, how do we remove from a vector? Erase, right? And do we provide that with a position, or we got to give it an iterator? Okay, so we would do array 6 elements, so it'd be this right here. Got it. So what we want to do is go down everything in basically donut box and consider that to be the first one. So that would be for, int I is equal to 0, I is less than, in this case, box.size, I plus plus. We go down here, and then the first time we're considering starting with uh, the situation where we're considering box 0. Let's say it's we're imagining it's of size 3, right? But we're going to be in a loop, so we're going to take care of it automatically. But the first time that's going to be v0, right? So we're going to do box, and it's going to be everything excluding that first element in the box vector. So we want to do box dot erase, really that code we just had, which was this here. But it's not going to be plus 5, right? It's going to be plus I. This is how we erase the first index in here. And what we're going to do, and we don't want to actually change this because we might down below want to change it in a particular way. Might actually want to do in one line. So it'd be, instead of updating what box is, we're going to do box.erase my vector.begin plus I. And this will be what the first thing is. Really, it's the vector that we had before, but the next time we go through and we want to look at the options, we can't consider the one we just went down. Again, recall the tree here. If we now want to go down the recursive path of either choosing v1 or v2, so this is going to be the next time we call this recursively, we should be given the options of everything except the current one we're going down, which is v0. So in the code back here, right, because we're erasing the first index, we're doing that because the next time through, we should only look at all the other ones, excluding the one we just, are currently keeping track of. So that's what we do there. And so what that means is we want to find the boxes where the box.erase is going to be, okay, so we're going to remove that. And then the current one, let's see, so that's the vector. We want to, do we care about the current box here? So we want to erase that. And then, I mean, I'd argue we don't need the current box because what we're kind of doing in an iterative approach here is we're considering every possible, we're basically considering every possible next available, we're considering every branch when we do this, right? We're looping through, we could go down this branch, we could go down this branch. Okay, if we're going to try to go down this branch, we should try it without having, with having one less thing in the box. So then we go down here, we do that, and then the next time through, we're kind of looking at all our options and going down that again. And so we could, for now, put in current box. We can go back to that if we want to tweak that, but really isn't needed, right? Because the only other thing that is important is keeping track of, all the solutions, because in the end we want to, return what those are. So in this case, oh, right, current box will be the vector. I get it. I get it. So current box is like, okay, if we keep going down this path, this is what the next one's going to be. This is going to be the next string. This is going to be the next donut. So we're assuming that we have some solution, and that's going to be, if I is equal to 0, it's going to be current box dot pushback. And we'll walk through the code again in a second. It'll be current box dot pushback, and we're going to add in here basically the box vector. and really the one we're looking at, because we're saying this is the current flavor that we're going to put in this order. So it's going to be box I, right? And then, so this is current box. The purpose of current box is to keep track of basically this collection right here. So the first time through, it's going to be a vector with just strawberry. And then if the next time through chocolate's the one when we go down this path, we're going to put down chocolate, right? And then if we go down and we do maple, we're going to do that. And that's going to allow us to basically collect all these things until we get to a base case, which we'll deal with now. The base case is going to be, you could do it a couple ways, right? If it's equal to the size of box, that means we've gone through every possible scenario. I think a cleaner way of doing it is if we go down this branch, right? First time we went through, there were 2 branches to go down. If we went down here, there's 1 branch to go down. And the next time we go through here, we're going to realize there's actually no more branches to go down. So if there's no other place to look, that would be the base case. We can actually just add it to a valid solution. Meaning if we go back here, and if you recall, each time we call this recursively and we go down the recursive path, it's what box was before, but with 1 less flavor, because we're saying, oh, we already take care of that flavor. So now let's look at the other flavors that we still have left. Well, if that's the case, then the base case could be if box.size is greater than, or basically if it's equal to 0, meaning there's no other places to look, meaning the branches is, there's no branches left to go down, then, really what we want to do is we are done, so we can return. But before we do that, the whole idea is we want to, store all these things. It's passed by reference, so we don't lose these as we, backtrack recursively. But, once, let's say we go down one path and we go down this branch and we're down the one that has strawberry, chocolate, and maple. We still want that in the future, so we need to store that vector. So it's going to be a vector of all these things. And then strawberry, maple, chocolate, right? Next time we go through and there's nothing there, we need to put that in there. So this is like our all solutions thing, just like in the homework 6. So it'd be like boxes dot pushback. And in this case, we're pushing back, the solution we have, which would be current box. Which, keep in mind, current box is just a vector of all these strings. It's just, we don't see it because donut box was a type def. I thought originally it was a class, which means a vector of donut boxes is a vector of strings, right? Because the idea is, as we kind of go through, like, okay, we're going to go down this path and we're saying we're going to start with this flavor. And now we're going to remove that flavor and only consider the remaining flavors. Okay, now we're considering that flavor. Now we're only going to consider the remaining flavors. And then once there's no remaining flavors to consider, meaning we've put together a possible combination, then that means the box.size, the vector of remaining variables, is equal to 0, right? And if it's equal to 0, that means we have a fully assembled combination, which means we can add it to the vector of combinations, which is just boxes. So that gives us boxes dot pushback and this. And then we can return because there's no other place to seek down here. And this will allow us to go through everything. Now, I also believe, let's go back to the problem set first. They also want us to set this up. So let's kind of get our driver function going, and then we can review it, answer any questions, stuff like that. So we have 5 boxes. It's going to take in, basically this box, which is going to be the same in the beginning, right? It's just all the flavors. And then as we go down the future, we want to consider those. We need to start with a current box for sure. But in the beginning, current box there's nothing in the current box. We're trying to do all these possible combinations. And so that could be, right, we want to basically do find boxes here with the existing box, with the boxes, that's an empty vector in the beginning, right? There's nothing really here. And we see donut box temp. Oh yeah, so it's actually right here. It's initialized. They basically, they were nice and gave us, I believe, the code for that. So it's really just plugging in the same things here, except that middle element is going to be temp. And remember, donut box temp is just going to be an empty vector, because in the beginning, we don't quite know what's going to be, in here, right? Or I mean, we do. It's empty, but we're going to kind of put in something one by one. Anyways, let's kind of go through the full thing. First, see if there's any questions, but then I can recap. Donut box is the type def Right. But the type for the first parameter is const. Would calling the function again while erasing still work? Let's see. That's a fair point, right? Donut box is const, so we can't quite remove that to consider the remaining options. I don't know why they did that. Okay, so we can adjust that. Let's think. We can't consider. I'm very surprised. It's like they want to make it harder for us. Hmm. Trying to think of a way around this. And implement your function, which should be recursive and modifies the vector argument to contain, which is this box is right here. We push back this in. We do find boxes. We print and print donut boxes, probably just a for loop where we output that. All right, let's think about this. How else can we go through and consider this? Really, the only change that needs to be made to this code is, a particular solution that allows us to make a connection um, of keeping track of things we've already visited. Now, there's a couple things we could do with this. The problem is we can't update the parameters because according to this assignment, it's like, well, these are what the parameters are, right? And these are what we have here. So we can't quite do this. If it's in a class, we could make a member variable and just have like a hash set, and that hash set could keep track of things we've already visited and haven't visited. Again, that we can't quite do that here. Oh, but what we can do is we actually do know what we visited, right? Because the current box allows us to see that. So what we could do, ah, current box basically pushes back what we're doing, but we could also check to see if the thing we're considering isn't yet in current box, right? So that could be all we have to do. Again, it's actually less efficient, but it's based on the restrictions of the assignment. We have to now do an O of n lookup. So all we have to change is basically we don't erase this because you're right. That's a great point. It's constant. So we'll keep this as a box. And then once we build the current box, we're only going to go down this path if we haven't done this before. And the way we know if we've done it before is if it's currently in current box. So we could just say if the thing we're looking for is in current box, which is the thing we're adding, and really if it's not in, right? So if box bracket I is, and we could have some helper function, so it's going to be if not in, right? Box I is not in current box. That means we can add it because that means we haven't seen it before. And then the code for that would just be, an in function. Again, it looks like there's only two places in this code for a function. I would do it in a helper function, but again, we have two boxes. So let's follow the PDF. And what we could just do instead is basically do something like this. We'd have a for loop that says for, in j is equal to 0, j is less than, and really we need to find one counterexample. So we'd say j is less than, and then we would assume in the beginning that, so let's see if it's in, so we'd assume in is true, right? And then we kind of go through, and the whole purpose of this is we're just trying to see if current donut has already been used by checking if in current box. So we loop through current box, right? I is less than current box dot size, j plus plus. It should be a j, not an I. And then what we can, we can do is when we're in here, if we figure out that the thing we're looking at, so if in this case, current box bracket J is equal to the thing we're trying to add, which is right box I. We're considering this as the next thing, but if we've already gone down it, then we don't want to. But if current box J is equal to box I, this means we actually have already taken care of it. So we don't want to actually try it again. So what we need to do is basically recognize that in is equal to false, right? Meaning it's not, wait, it means in is true, right? If we found that it's in here, we're assuming it's not in there, and then if it is in there, we're setting into true. And since we found that it is in there, we can actually break right here. We don't have to spend all this time looking at all these other, possible, you know, donut strings. We've already figured out it's in there. And then if in is true, that means that's a problem. So we can only do it when in is false. So if we haven't set into false, that means down here, if it's not in the vector, which is good, that means we can continue to go down there. Really what we can do is we want to basically, we're saying if box I, and it's not, this isn't a function anymore, so it's just gonna be if not in, right? Because that's now a Boolean variable up here. And if it isn't in there, that means we can add it to the current box, and we can now recursively call this again where the current box is basically the next one we're looking at, which is box here, right? So current box dot pushback box I. So that, again, this is less good because the code is less clean, right? It's more inefficient. But again, the removal is O of n, so it's probably the same efficiency. It's just a little more messy. Let's see. Can't you make, wait, what's this first one here? Can't you make a temporary vector contain the same stuff as the const box, but without the flavor we already have? Temporary vector. Yeah, we could. The reason I didn't want to change the parameters is because they were set here, right? So right. If this was in const, it would work, but we're kind of restricted to what the homework or what the practice problem is telling us as default input. But you're right. If we did have control over that, we could use that, and I honestly think that would probably be a little cleaner. But again, given that we're restricted to having something that's const here, and we can't make changes to box, then we have to adjust. And let's confirm, did we make any changes to box? We did, I think we only accessed it, right? We changed current box, we just kept passing box through. We looked at box, but we didn't make any changes. So that should be good. All right, let's recap because there's a lot of code here. Really, this first function here is to drive the recursive function, right? We're saying that this box is basically a string of flavors, and we're trying to basically see every possible combination, right? If it was just glazed and chocolate, there's only two solutions, right? Glazed chocolate, chocolate glaze. But what we're trying to do is if there's a collection of flavors, we want to rearrange them in every possible unique combination. And what we want to do is add it to this empty vector of boxes. So in the end, it's like a vector of strings that kind of shows us every possible combination we have. So to set that up, we need to also realize that as we're doing this, we're kind of going down some path that's going to show us if we start with this flavor, that leaves us these remaining flavors. And if we now try this flavor, that leaves us with even less flavors. And as we kind of build up this vector of string flavors that's going to represent one possible combination, we need a vector to keep track of that. And that's what this donut box temp is going to be, which up here ends up becoming the current box we're dealing with. Boxes is in the beginning empty. The base case of this recursive function is going to be when there's no other things to consider. So actually we can't do this anymore, right? Because we don't change box.size anymore. The whole idea is box is constant, but that's okay. Really what we just need to make sure is that current box is equal to the size of box, right? So if we said box.size is equal to current box.size, that means we have, an equal amount. We fulfilled, if there's five flavors, we're saying, and our current box now has five flavors, we've completed a full combination. And then if this is the case, right, we've kind of gone down this whole path and we found a solution. Boxes is supposed to be our vector of all solutions, so we would just want to add that to boxes. And it's basically going to be a vector of our current box, which is a string of the flavors of it's basically a combination. Donut box represents a combination of flavors that once we have a combination of every possible flavor that's unique, we'll add it to boxes. But, that's only when we have, a current box of five. The first time we go through, there's nothing in current box. The second time we go through, there's only one thing. And so we need to do it until we have a size equal to box dot size. And again, what that looks like is we consider just one of the flavors, but we have to consider the possibility of the first index being the first flavor or the next index being the first flavor up until how many possible flavors there are to consider in the beginning, right? And if we do this, now the next time around, we want to consider all the other flavors excluding the one we started with. And then later on, that's kind of the recursion. If we go back here, it is kind of convenient to remove it from a vector, but because we're limited to that, really our only indication of things we've seen in the past is by looking at current box, which is a vector of flavors that we've considered so far. So if we started, with, chocolate, what we should do is in the future, make sure if we now look at all the possible flavors to consider in box, we want to make sure it's something we haven't already put in current box. So in this case, if we loop through and chocolate is in there, that means we don't want to go through chocolate again because we want a combination, we don't want any repeats. So what we say is we're going to set in to false, and this is our way to see without a new function because the PDF's basically showing us two blocks of code. We kind of go through everything current box, and if we see something that is currently equal to what we're currently considering, which is boxes I, which is we're saying this might be the next flavor we should try. And we want to try it for every next flavor we can possibly try, which is where the recursion branch is coming in. And let's say in the end we go through and it's already in there. Well, that means we don't have to visit it. Let's just, try looking at the next flavor. So we go up and we continue the for loop. But if we go through and we're considering a flavor that we haven't considered before, right? What that means is, yeah, if we're considering a flavor that hasn't already been in current box, we want to recursively call find boxes with the same boxes before. It's okay because again, we'll check based on current box to see if we've seen that before or considered it before. This is our solutions. We always want to keep track of that. But the difference is current box is going to be what we had before, except, one level further where we're also having the latest flavor, right? Current box dot pushback box I just basically means, okay, you know what? We haven't visited V0 yet in our combination, so we're going to put that in here and go to the next place. And then once we're here, we have a couple options. And in our first iteration of the for loop, we're going to go down this branch. In our second iteration of the for loop, we're going to go down this branch. But, first time around, we look at this, we're like, okay, let's say this is chocolate, this is glazed. We're going to add glaze to the vector, and then we're going to go further down, right? And the next time through, that only leaves us with one option. How do we know we only have one option? Because if we go back to the code, we have a for loop and we can say, okay, we've already taken care of the index 0, and we've already taken care of index 1. So index 2 is the only one that still isn't in current box. Okay, and then we add that in. And then finally, we get to the recursive level where we're comparing the sizes and we say, okay, it turns out there's a donut box basically has, 5 types of donuts, and these are the donuts, and it's equal to 5, right? Well, it turns out here, our current box has 5 unique donuts in it. This is clearly a valid combination, so we need to add that to the boxes thing. And then we return to make sure this doesn't go on forever. And that should be the solution to question 1. Any questions with that? If not, we could also talk about, where is it? Just how to go about recursion, I think was part 2 to that question. Yeah, so some of the things we've talked about in the past, are 3 standard pieces of advice. One is obviously practice problems, right? You need to be able to, identify certain types of recursive problems and, practice them. Obviously, the site I recommend for that, is usually LeetCode, but really filtering by the recursive one. So let me just show you how you can get there if you haven't seen this before. Now, I can also tell you about how to walk through them, kind of like we did there. So give me one sec. So looks like my internet's a little slow. So if we go to, I can find it, recursion here, this gives you some really good practice prompts to work with that may be very helpful. So that's one place to go. And there's an integrator here so you can verify that this is good. Yeah, so yeah, this is what it's in right now. So how do you know the base case? Well, again, part of that, is working on practice problems. Another tip that I recommend is trying to think about, the how to approach it's different when you're reading a recursive problem versus writing a recursive problem. So if you're trying to read a recursive problem, I like to think of recursion as a stack of functions, right? Where if we have one function and we want to call it recursively, we're not going to quite yet consider this function until we, recursively call the next function, and we recursively call the next function, right? And then finally, if we go up here to a base case and we've completed that function, there's really only two ways you complete a recursive function. One is you finish every line of code of the function, or you use the return key. And then once you do that, you backtrack. And then now we're back to that recursive function before. And then we backtrack. We go to that recursive function before. And I think getting used to that pattern can help you determine the base cases. In terms of writing recursive functions, and then we can kind of see this as an example here. One of the ones we did a couple weeks back is kind of making this connection that if you understand how to probably do something in a while loop, you can kind of take some of that and transfer that knowledge over to something recursively. So for example, if we just wanted to print everything in a vector, right? If you want to do that with a while loop, you could say int I is equal to 0, right? We could say while I is less than, say it's vector v, right? V dot size. And we say, so say I is equal to, well, I is less than v dot size. And then, the incrementing, right, would do I plus plus. And then let's say the body, we're going to see out, in this case, vi. Well, really what's interesting here is there's three parts to this while loop, right? There's the condition, which tells us when to stop, right? There's the body, which is where we're actually doing the stuff repetitively. And then there's the incrementing that kind of updates what's going on for the next time around. In recursion, the condition is going to be converted to the base case, right? If you can think about things iteratively and think about how I would probably go about doing something like this iteratively, the condition kind of transfers to the idea of a base case. So that's another idea, or another recommendation. Kind of think about what the condition would be from an iterative standpoint, and that would help you kind of determine that this would be the base case. Right, the body is going to continue to be the body because there is repetitive acts with some, catch with recursion. And then, the incrementing will be, passing, as updated parameters. And what this means is if we have some vector, right, and we have some function called, like print vector, and we take in, as input, the vector we need to print, and then probably I, which represents the current one we're on. So we'd have some function before this to call it to drive the whole, recursive printing. What we can then do is as we go through, well, the first thing we got to talk about is the base case, right? We're saying that we want to keep on doing this while loop until I is less than v dot size. Well, the base case is going to be kind of the opposite. We're not going to say, how do we know we keep going? We're going to ask, when are we going to stop? So we're reframing the question. We stop when I is equal to v dot size, right? So if I is equal to v dot size, what we would do in this situation is, we'd return, we're done, we'll backtrack. However, the body is still the body, right? If whatever I is, we want to see out v bracket I, with a new line. And then instead of I++, we want to pass this as updated parameters, right? And so that would be something like, print vector with, a v, same as before, but I is going to be, a value higher. But again, if I gets too high, we backtrack. So really, I guess to answer your question, and then also I should say real quick that if we walk through this, it should be read as a stack of functions. So if we have a vector, right, and we have like 4 numbers in there, and the first time, I is going to be equal to 0. 1, 2, 3, 4, I is equal to 0. Well, if we go through, right, I is not equal to v dot size, so we're going to print out 1, over here, and then we're going to recursively call this. So the next level in the function stack is going to be what we had before, the same v, but now I is equal to 1, right? We didn't reach our base case. We're outputting 2, right? And now we're recursively calling this. And again, when we pop off the stack of recursive functions, there's only 2 scenarios, right? It's the scenario where either we've hit the return, right? Which means, okay, we hit return at this level of function, no more. We're back to the function we were at lower before, right? And that's one way. Another way is if we've completed every line of code in the function. A really good example is last time we were talking about, if you recall, the binary search tree. And if we do an in-order traversal down the binary search tree where we're like, okay, we want to go down here, we want to go to the left, right? And we want to do that in-order traversal. There's really 2 ways we backtrack down that tree, right? There's the situation where we finished every line of code, we go to the left, we see out, we go to the right. Or, if we've finished that, that's one way. Another way is if we're at the base case where the leaf is null, right? And in that case, we would also be done because we hit the return keyword. But to answer your question, the reason I bring up this example is the way you develop a base case is the same way you would develop a condition of a while loop. There isn't anything quite different other than just, getting very familiar with how you would take something iteratively and putting it together in a recursive statement. Because in the same way a programmer would think programmatically about how do I know when to stop a repeated block of code, I would assume, to some degree, right, you'd probably feel comfortable if someone told you to write a loop to solve a problem in a way that was probably reasonable to do, you'd be able to understand what the condition should be. When should the while loop end, right? In that same way, it's just getting familiar with how recursive code is carried out, which is, how do I envision these stacks of functions? And how do I kind of take, iterative code and converting it to recursive code? And how do I identify, recursive problems and, understand types of recursive problems? And in that same way, once you get the idea, the pattern, and the flow, I think it'll be a lot more comforting because you'll kind of think about the base cases in a similar way as you think of the conditions and while loops. Because again, it's like you're just asking when are you going to stop, or when is something special going to occur? And once you understand that pattern, it's really no different than understanding the special conditions in a while loop. So it's getting familiarity with base cases. I think it will certainly help. But again, getting familiar with that pattern will certainly help you. And I do think the practice problems on here with recursion will certainly help. I think those are really great just because you're getting used to those, and then trying to, once you implement the code, truly walk through and read it. So I think a really good one that we talked about last time was that in-order traversal. If you really understand how we traverse through that stuff, and how we went to the left, or then we output, we went to the right, and then we knew when to backtrack. Those are the things that are really helpful to understand. And once you understand that pattern, I really think it'll feel as comforting of trying to determine what the base case is as it is when you try to find a condition for a while loop. Yeah, let me know if you have any other recursive related questions, or something more general about how to go about that. But happy to answer that too. While you do, or if you do, I'm going to put a couple good hash table practice problems that I think I shared in the past, but they weren't relevant back then. But I'd recommend everyone here to try these out. They're very, I wouldn't say they're simple. They're very, I don't know what the best word is. It's generalized over everything that we kind of talked about and learned in lecture, which is both how to handle collisions, how to add stuff to a hash table, how to create a hash function. Really, it all comes together in these two problems, and it's for both of the types. So let's do hash table. There's design hash set, and there's design hash map, right? And the whole idea here is you just have to build an hash table class, right? How will we add some to the hash table? We're talking about today, what the structure look like. Would it be a vector of vectors? Well, it depends on how you're handling, collisions. And how do we see if something's contained? Well, that's running it through the hash function. I'd have some helper function down here called that we'd call a lot called maybe int hash function, right? Which will return some bucket value that we can put it in. This is basically how we would do it for a hash set. That one will probably be a little more simple because we don't have to keep track of keys and values. We put that in there. And then the hash map's going to be exactly the same thing, except now we're keeping track of two things, right? In fact, I would say the difference is the value is just, the key and value. This is now like an object, right? If we get to some place in the hash table, we're looking for the key, but we're getting back the value. We have a container that keeps track of multiple objects. So this would be designing a hash map. But do the hash set first, because the hash map's more complex. It has more levels of complexity you have to keep track of. But really, you can take the hash set code and tweak it to get it to work for a hash map. So I'll put this in here. I highly recommend you do these two problems. I think they're really, really good problems that help recap everything you've learned. I think if you can do this problem, right, and you can do it with open addressing, right, with the separate chaining, and then you do it again and you can do it with open addressing, you really understand the collisions, you understand how hash tables work, and I really think these two problems, although they shouldn't take, they should take less long than I think some of the lab assignments. I think it's the best summary I've seen of what's covered in the hash table lectures. So hopefully that's helpful too. Um, all right, I got like 1 minute or so, or I guess another minute I have in case anyone has any questions. So yeah, if you do, feel free to put them in. If not, I hope everyone has a nice week, does well on the exam, and that almost done with the semester in all courses, but more excitingly, almost done with data structures, which will be pretty sweet. So wishing everyone the best. You as well. Have a good one.